Now, let's draw the Lewis structure for the nitrate anion. Again, by symmetry, nitrogen would go in the middle and the oxygens go on the outside. Nitrogen has 5 valence electrons, each oxygen has 6, and because it's got a -1 charge, we're going to add an additional electron, so that's a total of 24 electrons in the picture. Connect terminal to central, uses up the first 6. Satisfy the octet rule for each terminal oxygen. And that's a total of all 24 electrons used up. The oxygens are satisfied, however, the nitrogen is not satisfied. So just like in the carbon dioxide example, we have multiple ways of giving the nitrogen the 2 extra electrons it needs. We could move a pair from this oxygen, and we'd end up with a double bond here, and the other bonds are still single. We could have chosen the oxygen on the left. So we're going to have a second resonance form. Or choice number 3, we could have moved a pair from the oxygen on the top. So again, all 3 Lewis structures are valid. All 3 have the correct number of 24 electrons. So these are resonance forms. So there's not one answer for nitrate. Nitrate could be drawn with the black structure, the red structure, the green structure. The reality is a mixture of the black, the red, and the green. All we can draw is these 3 possibilities. Diatomic nitrogen will have a total of 10 electrons in the picture. Only 2 atoms. Connect them together. Satisfy either the nitrogen on the left or the one on the right first. So if we start with the left, that one needs 6 more electrons. That's 8 out of our 10 electrons. So we run out of electrons by putting 2 more on the other nitrogen. So this nitrogen is short 4 more electrons. So we're going to end up moving not 1 lone pair, but 2 lone pairs. So we end up with a triple bond between the 2 nitrogens, and each nitrogen ends up with 1 lone pair. Now, whenever you make double bonds or triple bonds, it's important to remember the only reason we drew double bonds or triple bonds was to satisfy the octet rule. Also notice we never started with double bonds or triple bonds. We always started with just a single bond. If you look at all the examples we've done so far that have involved double bonds or triple bonds, you'll see some elements like oxygen, nitrogen are very common for double or triple bonds. The most common elements that make double or triple bonds are sulfur, nitrogen, oxygen, and carbon. So if you remember the mnemonic SNOC, whenever you're making double or triple bonds, those are the most likely. Now, they're not the only ones. For example, selenium can also make double or triple bonds. And when you read through the textbook, you'll see examples that involve elements that aren't sulfur, nitrogen, oxygen, or carbon. So this is not a rule. I'm not saying that these four are the only ones that make double or triple bonds, but these are the most common ones. For the molecules that you're drawing, check to see why are you making double or triple bonds, and the answer should be to satisfy the octet rule, and most likely you'll end up with these elements on both sides of the double or the triple bond. That example that I was talking about with selenium is in your textbook, example 10.16. So most common are SNOC, but that's not the only ones. One more example, strontium bromide. Now, the first thing you want to check is we have a metal and a nonmetal. So this will not be covalent bonding, this will be ionic bonding. And when you draw ionic bonds, we do not follow the 7-step procedure. Instead, we just draw our Lewis structures. Remember, strontium forms a +2 cation, and each bromine forms a -1 anion. The strontium starts off with 2 valence electrons, and each bromine starts off with 7 valence electrons. Each one of the bromines is going to steal 1 electron, so the strontium will end up with no valence electrons and a +2 charge. Then we have a bromine that has 8 valence electrons around it with a -1 charge, and a second bromine that also has 8 valence electrons around it with a -1 charge. So notice we're not connecting the atoms together. We don't draw lines. We only do that for covalent bonding.